Bonjour and welcome to the University of Lille. We are the students of Master 2 PhoCQS, Laser Engineering and Application. Today we have a course supervised by Professor François Anquet about metrology, and we will talk about the Sagnac effect. Let's go.
Okay, so first let's start with the theoretical background on the Sagnac effect. The Sagnac effect, first discovered in 1913 by French physicist Georges Sagnac, is as follows. He said that if we have a light source and this light source is split into two counter-propagating beams, these counter-propagating beams would have no phase delay between the two if we recombine at a point where their optical path would be at equal lengths. So here, for example, if we recombine, we would have delta phi equal to 0. But on the other hand, if we add now an angular momentum characterized by an angular velocity omega, this would create a phase shift between the two. So one beam would be in phase delay compared to the other, and so now we would have delta phi different than 0, and this new phase shift would be directly related to the omega, the angular velocity, and to the surface area of the optical path, and to the wavelengths of the light by the formula delta phi equal to 8 pi a being the area over lambda being the wavelengths, c being the velocity of light, and times omega, which is the angular speed. Now, we have decided to replicate just this, and now we will see with Anas how we did that.
Thank you, Shakir. Now let's make a quick sketch about our setup. We have here our laser that goes to our coupler, making the Sagnac loop, and goes back to our photodetector. This is the coupler that allows the beams to go from different directions. And here we have the photodetector. And here we have the Sagnac loop. And now we can move on to see the rotational table, how we made it using the 3D printer here in the Open Lab. Thank you. Okay, and now let's talk about the rotation system that we made using a 3D printer that we have here in the Open Lab. So for part 1, we have the bottom part that holds the optical table and also circular bearing from the inside. And for part 2, we have here the second part that holds the whole system on it and the circular bearing from the outside, allowing us to do the smooth rotational setup.
So now I will speak about the experimental setup. So here we have the 3D printed rotational base. And here I will show the components. Here we have the laser connected to the optical fiber, and then we have here the coupler, and is spliced with the optical fiber loop. And here we have also the second side of the coupler. First one is connected to the photodiode here, and the second one is connected to the laser here. And also the photodiode is connected to the oscilloscope. Thank you.
Okay, here we can see how the light is traveling. We can see that the light, the source of light is the laser, and after we have the coupler. And here we divide the light into paths. And finally, this arrived to the photodetector.
Once we are done with the setup, we can then connect the photodiode to our oscilloscope. And then when we rotate our platform, we can see that we obtain variations of intensity. Those variations of intensity can be translated into a delta phi variation, and then from this delta phi variation we can then get the angular velocity omega.